Hello everyone, I am Muhammad Tariqul Islam from University of Campinas, Brazil. Today I am going to present our work QoE Performance Evaluation Framework with 5G datasets. This is the agenda that I will cover in this presentation. First I will start with introduction, then I will discuss about some relevant background. After that I will cover the gaps in the literature and our contributions. Next, I will go through the details about our framework with experimental use case, and finally conclusion with some future directions. Introduction. Online video streaming traffic has become the most dominant application on today's internet. A large number of video on demand contents are provided by the OTT platforms such as Netflix, HBO. Recent studies from Cisco and others present that in future, video traffic will take a significant portion of total internet traffic. Due to the appearance of new network-intensive services such as virtual reality, augmented reality, cloud gaming, alongside the OTT platforms, upcoming 5G network is expected to support high throughput and low latency to enhance the overall quality of experience or QoE expectations. In 5G, one of the key challenges to adapt the increased growth of video streaming traffic and maintain smooth QoE. For the video streaming, the content providers adopt dynamic adaptive streaming over HTTP or DASH standard to deliver the video content, wherein adaptive bitrate streaming or ABS algorithms aims to detect appropriate video quality based on network function status so that user receive better QoE. As we know, QoE is user perceived experience that can vary based on user context, expectation, and environment. For video streaming service, among all the influential factors of QoE, network level quality of service or QoS KPIs such as delay, throughput, packet loss can directly affect application level objective QoE KPIs such as bitrate resolution stall, which later play a significant role to change the user subjective feedback. Therefore, upcoming network should ensure a QoE-aware network system to optimize the better video delivery through the network. For this reason, it is important to understand about ABS algorithms behavior for DASH video service, simultaneously the impact of QoS and QoE KPIs and their relations. In our work to understand the in-depth ABS algorithms behavior in terms of QoE and QoS, we present a data-driven framework for DASH QoE performance evaluation over 5G cellular network traces. The benefit of our work twofold. First, the framework is reproducible with a series of pre-installed DASH tools to analyze the state-of-art ABS algorithms by changing the QoS KPIs in different scenarios. Second, interactive notebook and binder service to make a live analytical environment to process the output dataset from the framework and compares the relationship of QoE and QoS KPIs. Background. Let's discuss about the logic behind DASH. DASH works by breaking the video content into a sequence of small segments, where each segment contains a short interval playback time. The duration of each segment could be between 2 and 10 seconds. Besides, each segment encoded with different bitrates and resolutions. At server side, the structure of each segment describes in a media presentation description or a MPD file. Specifically in DASH video service, a server hosts MPD file with corresponding encoded video segments. On the other hand, at client-side video player, ABS algorithms are responsible for dynamically select appropriate segments based on current network conditions. Client-side video player first download the MPD file and then it start to request each individual segment according to MPD information. The purpose of dynamic segment selection to adapt the changes in the network conditions and provide an interrupt-free video streaming service. ABS algorithms mainly built on three strategies: rate-based, buffer-based, and hybrid. The rate-based algorithms makes an estimation of bandwidth based on delivery rate of previously downloaded segments and choose the best quality for next segments. The buffer-based algorithms monitors the state of playback buffer before every segment download and select the appropriate segments. And lastly, the hybrid. The hybrid algorithms is a combination of both rate-based and buffer-based. Gaps and contributions. Although many studies have done on adaptive video streaming, but most of the work conducted on a specific video streaming service which follows a particular adaptation algorithm for segment selection. Therefore, we identify a gap for the comprehensive studies on state-of-art ABS algorithms. Besides, the studies have done on Dash video service with ABS algorithm, most of the work has a lack of reproducibility. The authors didn't mention their artifact for further reproduce. Moreover, existing works have given much attention to QoE evaluation rather than state-of-art ABS algorithms per segment QoS-QE relations. The QoS-QE mapping relation is necessary to deliver more evidence-based, higher quality video content through understanding how limited network resource can impact QoE of end users. To fill the stated gap, we provide a flexible framework for analysis of Dash video service supporting 5G cellular network traces. The framework is equipped with many options such as ability to change the video content for streaming, a range of different state-of-art ABS algorithms to compare QoS-QE KPIs, and a rich set of different evaluation scenarios. The contribution has two phases. In phase 1, it represents a multi-user reproducible streaming framework for data acquisition and processing. And in phase 2, it presents an analytical environment for results obtained from phase 1 for data analysis. In the next slide, I will discuss more details about both two phases. Phase 1, Multi-User Streaming Framework. The framework encloses with Mininet Wi-Fi, a network emulator, KD, a server for video content, Godesh, a video player, TCP dump, a network packet sniffer, and with few scripts, where Bash script used to emulate network traces bandwidth values sampled from 5G network at runtime. On the other hand, Python script used for processing per video segments QoE and QoS logs. Additionally, the framework uses Jupyter Lab, which is a web-based interface to enable Jupyter Notebook and terminal interactivity. Mininet Wi-Fi is a high-fidelity and fully controllable network emulator. It is a fork of Mininet extension. Network emulation is a technique to mimic the real network behavior over the virtual network. So in our work, we use Mininet Wi-Fi tools to emulate video streaming network scenario. We made a simple topology containing two OpenView switch 1 and switch 2, where a Mininet Wi-Fi node acts as a server through KD linked with switch 2, and multiple Wi-Fi nodes act as a video client using Godesh player linked with switch 1. We limit the link bandwidth between switch 1 and switch 2 from 5G network traces. The details about the Mininet Wi-Fi emulator available in following reference. To host Dash video content, we use KD Server version 1. KD is known as Web Server Gateway Interface. Currently, we use the animation video named Sintel as Dash video content at KD Server. We source this Sintel animation Dash video encoded with different bitrates and resolution from the following reference. The duration of each video segment of the Sintel video is 2 seconds. This Sintel animation video contains 8 resolution across 13 representation rate. Godesh. Godesh is a headless Dash video player. It is written in Go language. The main difference of Godesh player with other traditional players such as Dash.js, JPEG, ExoPlayer is stream video content without decoding. To stream video content without decoding makes Godesh more lightweight, memory efficient, and makes suitable for large-scale evaluation. In addition, Godesh supports different state-of-art ABS algorithms. In our framework, we utilize 6 state-of-art ABS algorithms from 3 categories. From the rate-based category, we use conventional and exponential algorithms. From the buffer-based category, we use BBA and logistic algorithm. And lastly, from hybrid category, we use arbiter and elastic algorithms. The details about Godesh available in the mentioned reference. Moreover, Godesh provides a log file with sufficient information about video streaming. Godesh provided log file contains per video segments objective QoE KPIs such as segment arrival time, stall, bitrate, resolution, buffer size, etc. Godesh is also able to calculate per video segment scores from 5 QoE model, including ITUTP1203 Mode 0 standard. A sample overview of Goddess log file is given here. To track the network traffic while streaming the Dash video content, we use TCP-dump, a passive tools from switch 1 interface. TCP-dump generates pcaps of network traffic for further analysis of network level QoS KPIs. Our framework contains a short bash script to emulate network traces values sampled from 5G cellular network at runtime. The actual 5G cellular network dataset collected from Irish mobile operator. The dataset generated from two scenarios, driving and static. The dataset is a composed of client-side KPIs including channel, context, cell-related metrics, and bandwidth information. For our framework, we only choose the bandwidth parameter from 5G traces dataset. We consider total trend traces from both driving and static scenarios, where the number of driving traces are 4 and statics are 6, with different bandwidth combinations. Linux TC, a traffic controller in Linux kernel, is used in our framework to change the link bandwidth after 4-second interval. The reason for select 4 seconds is that at least 2 video segments can download on the same interval without any interrupt. After video streaming, to process the generated log and pcaps by Godash and TCP-dump, we use a Python script to process the per segment QoE and QoS KPIs. The Python script is responsible for fetch per segment QoS KPIs from pcaps using escape library and fetch per segment QoE KPIs from Godash log files. After that, it merge both KPIs for per segment and export a CSV file. This Python script is executed using Jupyter Notebook. Phase 2 Dynamic Analysis Demo. In this phase, we analyze the dataset in CSV format obtained from phase 1 using Jupyter Notebook, as the CSV file contains per video segments QoS and QoE information. Hence, using the Jupyter Notebook, we can analyze per video segments impact of 5 QoE models output, 7 objective QoE KPIs from Godash. They are arrival time, delivery time, stall, delivery rate of network, segment size, representation rate or bit rate, and buffer level. And also 3 QoS KPIs from pcap. They are uplink RTT, downlink throughput, and downlink number of packets. In Jupyter Notebook, we use interactive widget library. Interactive widget gives control over the data. We can change inputs without needing to rewrite or return the code. Thus, it makes Jupyter Notebook dynamic from static to explore and visualize the data. Researcher can easily visualize per video segments KPIs output by changing the input combination. Here we can see how input and output are changing dynamically over our given notebook. Experimental use case. For ease of use, the framework includes in a virtual machine or VM with all Dash related software and dependencies. Sometimes dependency hell makes the environment setup quite impossible, though the exact information of software packages version available for reproducing the work. Hence, to avoid dependency hell and simplify the execution of work, we provide our entire Dash streaming framework through the VM. This is our entire framework outline inside the VM. Here we can execute 3 tasks: data acquisition, preprocess, and analysis all together. For ease of use, the framework integrates the provided VM with Jupyter Lab. Jupyter Lab is a web-based interface that enables Jupyter notebooks and terminal activity. We can complete multiple tasks under single browser tab. Here the terminal helps to execute our streaming topology, and the notebook helps to preprocess and analyze the data. We provided a video demonstration to use the VM with a single combination for data acquisition, preprocessing, and analysis. Our framework is flexible. One can change the combination according to their needs. Scanning the given QR code, one can find that video demonstration. Now I will showcase important portion from that video demonstration. Inside the VM, this is our framework folder structure, which contains 3 folders: testbed, notebook, and data. So inside the test bed, we have mininet Wi-Fi topology, Go-Dash, 5G traces, and Bash script. These are the 10 5G traces, and inside the notebook folder, we have data preprocessing and data analysis notebook. And inside the data folder, we have another two folder, raw and process. The raw folder contains Go-Dash and pcaps log file. This folder contains CSV file. This is the KD with the corresponding dash video content. Now you can see Jupyter Lab interface, where we open terminal to execute the streaming topology. So here you can now see the streaming is started. Streaming end. So after streaming done, so Go-Dash log and pcaps stored inside the raw folder. This is the script for data preprocessing, executes in using notebook. This is notebook for data analysis. In addition, we also use another notebook. It's called executable, to execute both data preprocessing notebook and data analysis notebook in a single notebook. So after data preprocessing notebook execution, we will get CSV file like this. And lastly, data analysis using obtain CSV file. Now to simplify dataset generation for the paper, we assess the impact of 2 and 3 concurrent clients streaming for 2 minutes from the same server, where for link bandwidth we use total 10 traces of 5G network. You can see one portion of generated data. In the paper, we present rate-based algorithms behavior in terms of different KPIs output. Here we can see 3 KPIs output for fast client when 2 concurrent client is streaming. For driving mobility, when bandwidth range between 6 to 14 Mbps, conventional rate-based algorithm slightly perform better than exponential rate-based algorithm. Here we can see at the beginning of the stream, both conventional and exponential rate-based algorithm suffer less stall. As a result, both algorithms gives higher P1203 modes at the beginning of the stream. And for per segment RTT, both algorithms have same RTT pattern. This is the result for another driving traces bandwidth range between 0.5 to 3 Mbps. Due to less bandwidth, here we can see both rate-based algorithms overall performance were poor than previous scenario. If we compare the RTT and stalls value with previous scenarios RTT and stall value, we see both of the RTT and stall values were comparatively higher than previous scenario. Thus, for the current scenario, the overall P1203 modes decreased. For further analysis of generated dataset, we moved both notebook and dataset to GitHub from the VM. As GitHub only supports the notebook and data in static mode, therefore we utilize the binder service to convert the read-only notebook that uploaded at GitHub into live executable environment for data analysis. This is the outlines of binder service for further data analysis. We also provide a video demonstration on how to use binder service with our dataset and notebook. We have released all the remaining code in GitHub link used for processing and analysis the dataset for reproducibility beside the VM. All the update about the framework will be available in the given GitHub link. Conclusions. In this work, we present a reproducible framework and live analytical environment to generate, process, and analyze the part segment QoS and QE KPIs for Dash experiment using different state-of-art adaptive bitrate streaming algorithm. In future, we plan to include other parameters impact from cellular network on Dash video service. And finally, extend our framework by using traditional supervised machine learning algorithm to make a QoS to QE correlation model for QE estimation. Thank you. I would be happy to answer any questions.